I mean, this is a person who not only did some amazing math, but also contributed to physics and computer science and economy. Some say he's also the inspiration that Peter Sellers had for Dr. Strangelove, because he actually turned out to be quite a bit of a hawk at the end of his day, and well, a complex person, but clearly very interesting and extremely, I mean, brilliant is almost too weak a term for it. Okay, so let me prove the bicommutant theorem, and the way that I'm going to do it is to prove that the double commutant lies inside the strong operator topology. That's the same we know as the weak operator topology closure, and this is contained then in a double prime. So this is the goal, and this one we've already seen. Actually, I think I'm using the easy direction of this, but let's not dwell on that. And then I have these two inclusions that I need to establish, and the one to the right is the easiest one, so I'll do that first. So how do I prove this? So I'm going to establish that the weak operator closure of A is contained in the bicommutant. So we just need to prove that a double prime is weak operator closed, because then of course we have the containment, since the closure is the smallest closed set, that weakly closed set that contains A, and we've seen already by the observation, I guess I'm using that here, that A is contained in a double prime. And to do this, we can sort of go directly. So assume we have a net T alpha going weakly to T, and T alpha lies in a double prime, and then the goal is to prove that T also lies in a double prime. So fix some S that lies in a single prime. We must prove that T and S commute, right? Because since S is arbitrary, if we can prove that T and S commute, then we've proved that T is in the double commutant. So we take some vectors x and y in H, and then note what happens if you take the difference between ST and, oops, to correct this, I wrote ST and ST, I mean ST and TS. I take that operator and apply it to X, and I take the inner product with Y. And now I can write this as as two terms, STX comma Y minus TSX comma Y. And then I'm also going to move the S to the other side over here, and then TSX comma Y. So the reason why I've done this is that now you can see that these are really the kinds of objects that we know how to deal with in the weak operator topology. Because I know that I have some vectors here, they're called X, S star Y, SX, and Y. But we know that since we have the weak convergence in the weak operator topology from T alpha to T, we know that all these inner products will follow suit when we let T alpha go to T. So this is just the limit over alpha of T alpha X S star Y minus T alpha, oops, T alpha SX comma Y, maybe put some parentheses around. Simply because these are the functionals that we've used. I mean, the functionals that we used to define the weak operator topology. These are exactly the ones that send T to the inner product of T. I'll use some other letters, Z and W. Right. So these all have to be continuous in order to. That's how we define the weak operator topology. So we know that since T alpha goes to T in that topology, T alpha Z inner product W will go to T Z inner product W, and then we're applying it with Z equals first X and W equals S star Y, and then Z equals SX and W equals Y. Right, so I'm using the star to move the S away from the T so that I can see that I can use the topology, convergence in the topology that I'm working with. But the point is that now I can just move things back again, because I mean it's the same expression independently of whether I have T or T alpha. So I can move everything back, and then I have ST alpha minus T alpha S comma X 0. And of course this is 0, because I've assumed that T alpha comes from a double prime and that S comes from a single prime, so they commute. So the thing that I have here is actually 0 operator, so everything is 0. And that's enough, as we've seen several times in the course, that's enough to conclude that this operator here is 0, and that's what we wanted to prove. Okay, so this was the easy implication, the easy containment. So now we need to deal with the other one, so the one that I'm calling number 2. For that we need a little bit of preparation. So let's do this first. So we need to look at the relation between a projection and the subspace that it projects onto. So I have a projection which is an operator in B of H. So projection means that P square and P star are the same as P. And M is a closed subspace of H. And you can sort of go back and forth between these two pictures. If you have a projection, then what you can do with it is that you can send it to the subspace, which is simply the image of P applied to H. And if you have a subspace, you can generate a projection by sort of summing of the inner product between X, EI, where EI is a basis for M. So we have a way of going back and forth between these two pictures, if you like, of a projection or a closed subspace. It's more or less the same. And we need to think about how this relates to commutativity. So that's the point that I'm trying to make here. So let's fix some operator in B of H, any operator, and then let me make two observations. So the first one I'll call Roman I. That is that Tm is contained in M if and only if PTP is TP. And the second one is that Tm is contained in M and that T star M is contained in M. I'm claiming that that's the same as saying that PT is TP. So you see, on the left-hand side, I have something about M. I have something about invariance of M in the sense that, T will send M back into itself, or T star will send M back into itself. And on the right-hand side, I have some sort of commutativity conditions that, of course, will be relevant when we start studying the consequences of working in the bidual. So these are fairly easy to see. So let me just argue for them. So one from from left to right. Note that if x is any element in H, then TPX is in M, because PX is in M. M is exactly the image of P, and by assumption T sends M back into itself, so TPX is in M. But then when I apply P to TPX, nothing happens because P is a projection down on M, so when I apply P to something that is already in M, it stays put. So this will be the same as TPX, right? And this is for any x, so PTP, the operator, is the same as TP, the operator. To go the opposite way, for number one, when I take some y that lies in M, we may note that y is py. For the same reason as before, if I'm already in M and I'm applying the projection, nothing happens. So what happens when you look at Ty? Well, Ty is the same as Tpy. By assumption, this is the same as Ptpy, and that lies in M because of the leftmost P, which sent everything inside M. Right. So this is how you see this. What about number two? So number two, to go from left to right, we use 1 to see that PTP is TP, because I've assumed that TM is sent back into M, so that tells me that PTP is TP. But I also now have the assumption that T star sends M back into itself, so I also have that PT star P is the same as T star P. But the latter is also that PTP is PT, because if I take stars on this thing here, then of course the equality still holds, and if I star through on PT star P, I get PTP. If I star through on T star P, I get PT. So I have that PTP is both TP and PT. So, oops. So TP is PTP is PT. And this one, I'll just write similar. It follows by the same argument. You can sort of stick together the information that I have from T and T star separately. Okay, so this is sort of easy to see, but it's really a key observation. That's how we make a connection between the commutativity and something that is a little bit more geometric in terms of the behavior of the underlying Hilbert space. I should perhaps mention that these things have names. So this is called that M is an invariant subspace, and this is the same as the space being reducing. We might return to these terms later on. Okay, so now we're ready to do the proof of the inclusion, and we will do it in the following way. This is the claim that I'm trying to prove. A is strong operator dense in A double prime. So this is sort of, I don't know if that's a reasonable drawing, but we have, A sitting inside A double prime, and then what I want to prove is that when you look at the closure of A in the strong operator topology, it contains all of A double prime. And this I want to do in the following way. So whenever I have a neighborhood of a point in A double prime, I claim that it contains something from A. Right? So it's sort of a classical denseness property. So what I want to prove is whenever I have a T in A double prime and an epsilon and some vectors in H, then if I look at the appropriate neighborhood of T, so that would be the S's lying in A double prime, such that the distance between S and T compared on the xi's is less than epsilon. This is what a neighborhood looks like in the relevant topology. Then that intersects A. So this is what we need to prove. And the way I'm going to do that is to use the prepared observation to get something that looks a little bit like this, and then use a trick to get the statement that we're after. So now I'm going to do something which is not directly aimed at the claim. So I will call this an aside to avoid confusion. So let's do it in the following way. So we fix some vector x0, and we consider something I will call M, which is all the elements of the form XX Sx0 in the Hilbert space, where S ranges in A, and then I'm going to close it off in the norm topology on the Hilbert space. So this, of course, is a closed subspace. It's a subspace because A is a subspace, and it's closed because I closed it. We can use the preparation. So we note that when T is in A, we have that Tm is contained in M, and also that T star M is contained in M. And why is that? That's because an element in M lies in the closure of elements of the form Sx0. So if I apply T to one of these elements, I need to know that this is inside M. This is obviously inside M because I can just write it this way, and Ts is in A because A is a C-star algebra, and T comes from A, and so does S. So, and then I just need to close off, and that is easy. And I can do the same with a star, for more or less the same reason. This is the only place in the proof that I'm using that I've asked that A was a C-star algebra, but this is where I'm using it because I know that T is in A. So because I know that A is a C-star algebra, so is T star. And because T star is in A, then so is T star S, and so this is in M, and this is in M for the same reason. Right? So, I mean, it's not enough to check that T sends Sx0 back into M, but then after I've done this, I can use continuity of T and the fact that the Sx0s are dense in M to get the conclusion that I need. So when P is the projection corresponding to M, we get, by my claim number 2 above, that PT is TP for any T in A. Right, so hence P is in the commutant of A. Now fix a T which is in A double prime, and note that T commutes with P, because by definition T is in A double prime if it commutes with anything from A single prime. In particular, it has to commute with P. So by 2 again, T sends M back into itself. So finally, we note that x0 can be written as the identity times x0, and the identity is in A because A is a C-star algebra with the same unit as I emphasized before, so this will lie in M by definition. So Tx0 lies in M. In other words, Tx0 lies in the closure of elements of form Sx0 S in A. So we conclude something I would like to call perhaps claim minus, because it's not really what I want, but it's in the same ballpark, namely whenever I have a T in A double prime, I have an epsilon and I have an x0, then the intersection between the elements in A double prime that are close to T relative to x0 and epsilon, that is a very special kind of neighborhood of T that has a non-zero, non-empty intersection with A. Right, so you see, I've sort of proved the claim, but only in the very special case when there's only one vector in the neighborhood, and that's not enough, right? So I'm going to have to work to get the general case to get from claim minus to claim. So to do this, let me just put some colors on this. So this is my claim, and this is my other claim. So it remains to go from claim minus to claim, and we will do this using a technique which is usually called amplification. So the idea is that we sort of take all the information in the n tuple that we need in the claim, and we bake it into a single element in a bigger Hilbert space. So this is the amplification. I think it's fair to call it a trick, which all of this goes back to von Neumann. So we now have T in A double prime, like in the claim. We have an epsilon bigger than 0, and we have an n tuple of elements in H. And this n in the n tuple, let me use highlight. This n we will use to make a new Hilbert space. So we consider a Hilbert space that I will call Hn, which will just be a direct sum of n copies of H. And we will define a map called phi, taking a bounded linear operator on H into a bounded linear operator on Hn by sending phi of t into a matrix which is diagonal, just contains t down the diagonal in setting. So I mean, in a sense, what we're thinking of matrices over B of H. That's an efficient way of doing it, but if you don't like that, then really all I'm doing is I'm saying I will take an operator in B of H, I will define a new operator in B of Hn, and the way it works on an element in Hn, which you might think of as a column vector y1 up to yn, that is going to be the matrix multiple of y1 up to yn, like this, and that just becomes t individually applied to each of the entries, right? Just like we would do in a matrix multiplication with a simple-minded matrix, which is just a diagonal with the same element repeated down the diagonal. So the real point of doing this is that this n tuple, we can put this together into a vector, x1 up to xn. And now the idea is that we're going to use the limited claim, the claim minus, on x underline, which is just a single element, right? So the difference between the small claim and the big claim is whether or not we have one element or several. And this is how I'm going to solve this problem. I'm going to take my n elements and think of them as one element in a bigger Hilbert space, and then apply the limited claim. So we note that if we take phi of A, that is a sub C star algebra of B of Hn, because it's closed under all the operations. And also note that phi of A double prime is contained in phi of A double prime. So I'm claiming that things in the bicommutant of A will be sent into the bicommutant of phi of A under phi. So let's postpone this for a second, and I'll return to it later. So now by claim minus, we have that if we look at a neighborhood, see, maybe I'll write it like this. So these, I'll use S underline as the name for a generic element in B of Hn. So the set that look like this, where the distance between S underline applied to X underline and phi of t applied to X underline is less than epsilon, that has a non-trivial intersection with phi of A. Right, so I'm using claim minus, and I'm just using it verbatim. My x, what used to be x naught, is now x underline. What used to be A is now phi of A, and what used to be t is now phi of t. And of course, this is sort of the thing that I've postponed. I need to know that phi of t lies in the relevant bicommutant of phi of A. So this we'll have to get back to, right? But let's just expand on what this means. So there is an S in A, so that the distance between phi of S against X and phi of t against X is less than epsilon. What does that mean? It means that when we're, let's just think of this as a vector, right? So this is sx1 down to xn minus tx1 down to txn. This norm is less than epsilon. And of course I'm using a Euclidean norm, so this will be like the sum of the sxi's minus the txi's square from I equal 1 to n is less than epsilon square. Right? I've taken squares to avoid the square root. So that means that sxi minus txi is less than epsilon for all I from 1 to n, proving the claim. Right? Because that means that in the original A, we have found an element S, which is close to T, not just on a single element, but on the n-tuple of the elements up to epsilon, proving that there is an S in that neighborhood as we wanted. But I still, so there's the postponed observation. That is the only thing I need to do now, because I proved the claim, right? So the claim means that A is strongly operator dense in A double prime. So that means when you that A double prime has to be contained in the strong closure of A, which was the implication that I needed. So let's just see what it means. So what does it mean to be an element of phi of A double prime or of phi of A prime? And in fact, the last question is sort of the key. So let's fix some S underline that lies in phi of A single prime. What does that mean that it lies in phi of A single prime? It means that if I take S and multiply it by phi of T, I get the same if I do it in the opposite order. And what is this? Well, this is a generic n by n matrix of operators that I'm multiplying by a very special matrix, namely one that has T down the diagonal. And on the other side I have T down the diagonal, and then S11, S1n, S1, Sn, lots of dots. And when I multiply this out, this will just be the matrix whose all entries look like Sijt. And here it will be the matrix whose all entries look like Tsij. Right? And that has to be the same. So we conclude that S bar is in the commutant of phi of A, if and only if all Si's, Sij's of course, lie in the commutant of A. Right? So it just needs to commute with all the elements in A. Sort of, I mean, it has to be a matrix whose all n squared entries all commute with A. So when T is in A double prime, we see that phi of T is in phi of A double prime, right? Because it commutes with anything in phi of A prime, because anything in phi of A prime is a matrix whose entries all lie in A prime, and hence by definition they commute with T. So that concludes the proof of von Neumann's bicommutant theorem.